Presenting our machine learning final project for INFR 3700. Today we are using a data set regarding diabetes and digestive and kidney diseases. So basically, the objective of the data set is to diagnostically predict whether a patient has diabetes based on certain diagnostic measurements included in the data set. Several constraints were placed on the selection of these instances from a larger database. In particular, all patients here are females at least 20 years of age and they have a Pima Indian heritage background. So within the submission, we're going to include a data set as a CVS file. Some of them are independent and some are only target dependent variable outcome. Insight on the information that we've collected. From the player plot shown below, it is clear that glucose level plays the most important role than any other feature. On the next page, we can see some more insight. Skin thickness, insulin, BMI, the age, and the diabetes from the data that we have collected. And clearly you can see that glucose is the most important role. And looking at another instances using inference, we can see over here with age being on the x-axis and density on the y-axis, we can see that there are more young people in the data set, majority of whom who have a BMI between 30 and 40, which indicates that most of them are obese. The majority of people use fewer than 200 units of insulin. Most people have skin thicknesses between 20 and 40, and most people with blood pressure between 60 and 80. You can see that over here we've prepared the data to better expose the underlying data patterns to machine learning algorithms. So at the bottom you could see that we've kind of taken all the different variables and information that we've gathered and put it all in its own separate charts. It can be a little overwhelming information to see, but however, it kind of gives it a very precise descriptive information of all the information that we have collected. And the different colors you can see over here are the different outcomes, blue being 0 and orange being 1. And this kind of recaps everything that we have gathered in a more precise, detailed manner.
Predicting diabetes. Why should we? Well, machine learning has actually been used to help doctors diagnose patients using similar metrics used in our dataset. This can provide helpful insight for patients before human interaction is even needed. So filling out an online form can give patients helpful insight on their health status. As well as the fact that if more data is collected over time, the better we can predict in the future. We will use supervised machine learning in our assignment, as you can see, and the more supervised information we provide the machine, the better it will be at predicting.
We have used 4 different machine learning algorithms to evaluate our data to predict diabetes with respect to the individual categorical data types. We achieve this by first understanding the definition of diabetes, which, regarding our data set, is mostly dependent on the blood sugar levels. However, each factor measured by the data collectors has an impact on the machine learning model. Thus, we need a model that can take each input and produce a dichotomous answer. So as you can see, this is our final result in our comparison table. On the left, you will see the model names, LR being logistic regression, RF being random forest, DT being decision tree, and DNN being deep neural network. The confusion matrices are listed beside it, which we were able to use to calculate our accuracy, precision, recall, and F1 scores. The first model I wanted to discuss was the logistic regression model. This model is very good at taking large sample sizes with diverse factors and predicting strictly binary or dichotomous answers. This model performs quite good with the highest accuracy in relation to other algorithms. This model also has the highest precision at 91% and an accuracy of 82%. It also performs every other model in the evaluation of F1 of 87%, which can be interpreted to being the best predictive model. The second model I wanted to show was a random forest model. This model is supervised, which is ideal for our data set, as we have the results for each prediction. The model builds many decision trees on samples and produces a result that reflects the majority result. This model is the second best model with an F1 score of 84%. Many predictive models for diabetes will use a random forest model. The third model I've created is the decision tree model. This model only differs by the random forest model by being more simple and more susceptible to overfitting. This model performs worse with this data than the random forest decision tree. This model is the third best model with an F1 score of 82%. The last model I created is a DNN. This model performed overall the worst out of all the other models. This is not surprising for the data, as a decision tree model outperforms DNN models for classification most of the time. This model is the worst model with an F1 score of 75%. So what an F1 score is essentially, it takes the combined precision and recall of a classifier into a single metric and then taking their harmonic mean. We can clearly see that logistic regression model outperformed the other models in the F1 calculations. The metric indicates overall predictive performance. This is one graph I've generated from the logistic regression model. This shows the coefficient of correlation by feature. So as we can see, pregnancies is positively correlated, around 0.3. Glucose is the highest, above 1. Blood pressure is negatively correlated. Skin thickness is also positively slightly. Insulin is slightly negatively correlated. BMI is a very big indicator. Diabetes pedigree function is also a fairly larger indicator, and age is also a good indicator as well. But as we can see, overall glucose has the highest correlation. The next graph I generated for the logistic regression model was the receiving operating characteristic curve. So what does this tell you? It pretty much shows you the trade-off between the sensitivity and the specificity. So classifiers that actually give you a curve closer to the top left corner indicate better performance. The third graph I decided to create was a precision recall curve. So what this shows is the trade-off between precision and recall for a different threshold. A high area under this curve represents both high recall and high precision, where high precision relates to the low false positive rate and high recall relates to the low false negative rate. The last graph I decided to show was the confusion matrix by percentage. So this was a matrix that we used to calculate all of our other metrics, and it's broken up by percentages and color mapped.